So today we are going to look at electronegativity. It is roughly on page 150 of your notes book, or at least my version of it. This is a little chemistry joke. So we have polar bear in the water, help, help, I'm dissolving. Brown bear saying, but bears are insoluble. And polar bear saying, that's easy for you to say, but you are not polar. And hopefully by the end of the day you will have a little idea what polar means in a chemistry sense. And eventually the joke will make sense once we go on to intermolecular forces. Now, we have already talked about the types of bonding when we started covalent bonding and we coloured in our periodic table. So we know that there is covalent bonding and ionic bonding. We know from when we coloured in our periodic table that for elements to covalently bond, they're usually on the right hand side of the stepped line, and for things to ionically bond, you will have something on the left hand side with something on the right hand side. We also have a definition for covalent bonding, and that is where electrons are shared between atoms. Okay, so today when we talk about electronegativity, we're going to be talking, electronegativities help us to work out what is the type of bonding that's between elements. And we're going to now subdivide covalent bonding into two types by the time we're done, and there is only one type of ionic bonding. So that is our plan for today. So if we look at these two molecules in terms of symmetry, which one is symmetrical? So oxygen would be written like this, HCl would be written like this. You could represent the double bond in oxygen very simply, two shared pairs like this, and for HCl you could represent it like this. So how do you tell something is symmetrical? Well, for starters, you look at what are the elements that are involved. So for oxygen, it is atoms of the same element, whereas for hydrogen chloride, we have different elements here. And then we look, what's that going to do in terms of symmetry? So if you have atoms of the same element, they are going to be a symmetrical molecule. So you can literally draw a line down this and both sides are going to be the same. Whereas for the hydrogen chloride, it's asymmetrical. And if you were to draw a line down the middle, well, they're not the same. There's not the same number of electrons on both sides of that line. So that makes it an asymmetrical molecule. So both of these are going to go into your little boxes up here. Now, one of the things that you can tell sometimes from just looking at a molecule is whether the electrons are shared equally, but can you be absolutely sure that that is the case? And to do that, we use what's called electronegativities, and we have to do a subtraction, a tiny piece of maths to work out which thing is more electronegative. Now, if you have a look at page 8 in the front of your book, and there's also a set of tables at the very end of your book, you will find the electronegativity kind of version of the periodic table there. And the definition of electronegativity is that what it is a relative measure. So it's not a real full-on, I would sell my soul because it's right. It is a relative measure of attraction. So these electronegativity values are numbers that, I'm not going to say they're made up, but essentially they're assigned to each element. So it's not a real full-on proper measurement. It's just assigned values. So electronegativity is the relative measure of attraction that an atom has for the shared pair of electrons in a covalent bond. So that is your definition of electronegative. So there'll be always if there is a electronegative element in a compound, one of them will be electronegative and there will be others that are electropositive, and we'll explain what that means in a second. So please make sure that you have the definition in the box and that you're able to vomit it back up for the SEC. And if you look at your electronegativity table, so that's page 8 in the front or in the very, very back, you will see that the numbers are going to have a definite trend as you go across a period and down a group. So take time for yourself now to have a look and see what is the trend, what happens to the electronegativity value as you go across a period, and what happens as you go down a group. Now, I would just like to point out here, so potassium is what you would call electropositive because it has a very low number. So the rule is the bigger the number, so you might like to write down as your side. So the bigger the number on that table, the more electronegative it is. It's going to go En for electronegative. So that's what you're looking for in your table. And what you should have found is that as you go across a period, your electronegativity values are increasing, and if you go down a group, they will decrease. But essentially all of the values are kind of increased towards fluorine. Okay, so we've seen trends before. We've talked about atomic radius, we've talked about ionization energy, and now we're going to talk about trends in terms of our periodic table. So again, this is just the list of the values, and the bigger your number up here, so this is the most electronegative is fluorine, and your least in this example is potassium. So that makes potassium more electropositive, okay, in terms of its measurement. So least electronegative. So we have to talk about our trends, or the factors which influence electronegativity. And they're the exact same things that influence ionization energy. So we talked about atomic radius before. So if you're a really, really small atom, you will have a real strong attraction for that shared pair, so you will be more electronegative. In terms of nuclear charge, the bigger the charge in the nucleus, the more electronegative it's going to be, because the nucleus will pull all those electrons towards it. And in terms of screening effect, the greater screening effect means you're going to be less electronegative, so the element will find it harder to attract the shared pair of electrons to it, primarily because the outer shell electrons are further away from the nucleus. So the nucleus isn't going to be pulling them toward it, so therefore they'll be less electronegative. So if you can kind of get your head around those three things, then that's going to help. One of the questions they love to ask, just as they did for atomic radius and ionization energy, is state and explain. So it is state and explain as we go across a period. So the state part of this is what happens to electronegativity, what's happening to the number. So as we go across the period, electronegativity is increasing. So those values on page 8 are increasing. The explain part now is, we did it for ionization energy, exact same three things. So what's happening across the period? Our atomic radius is decreasing, there's an increase in the nuclear charge, and there's no change in screening effect. And again, you give all three parts, you don't know what the mark scheme is going to be like, and we've seen this before for ionization energy. This is the exact same explanation as for ionization energy, and ionization energy also increases across a period. So if you can remember one, you can remember the other. So now we go down a group. So down a group, our electronegativity is going to decrease down a group. And what's the reason for what happens down a group? So it has to do with the fact that your atomic radius has increased, has to do with the fact that we now have an increase in the number of energy levels as you go down a group, and the fact that there is an increase in the screening effect. So that nucleus is blocked off the further an element is down its group. So again, this is the exact same as it was when we covered ionization energy. And again, I ask you to refer to page 8, or the electronegativity table, and if you look at it in your book, fluorine is the most electronegative element, and the reason for that is because it has the largest value. So if you look at the numbers, the number for fluorine is the biggest number. So that's what makes it the most electronegative. And the reason why it is the most electronegative is because it's the smallest atom and it has the greatest shielded charge. So what does that mean? That means its outer electrons, so the ones it's going to share, they're the closest they can get to the nucleus. So if you're in the next period down, you're now further away, you've got that shielding, and that has an effect. So the closest they can get to the nucleus. Okay. So just use pieces of information. Fluorine, a gentleman got a Nobel Peace Prize for reacting fluorine with xenon, and the reason he could do that was because fluorine is so electronegative, it pulls the electrons to it. So we've done our state and explain, we've seen our trends. Now we're going to see what we can use the numbers. What's the point of the table? So the numbers allow us to determine the type of bonding within a molecule. So if we look at oxygen now, how do we use it? So we're trying to find out what type of bond is in oxygen. How do we do it? So we look at the electronegativity values. And if you look at the value of oxygen, it is 3.5. So I have my elements in my bond are an O and an O. So each O is going to be worth 3.5. So 3.5 take away 3.5, it gives me a value of 0. And there is a rule, and you need to know this rule. So the rule is when your electronegativity values are less than 0.4 or less than or equal to for you, but so I'll just give you that little symbol, then the bond is described as being non-polar covalent. And what that means in this instance is not only does oxygen have a non-polar covalent bond, but the molecule itself will be non-polar covalent, and it has to do with the fact that it's symmetrical. So we'll get into that at a later stage, but I'm putting it in here now for completeness. And our definition for non-polar covalent, so we said covalent bonding was electrons are shared between atoms. When it's non-polar, they are shared equally. And you'll see in the minute what unequal sharing means and why that then is going to be polar. Okay, so we carry on and we now look at HCl. So we're trying to figure out what is the type of bonding in HCl. So again, we're going to use our electronegativity values. So H is 2.1 and Cl is 3.0. So usually when you do your maths, it's the bigger number is always going to come first. Okay, so it's going to be 3.0 take away 2.1. 2.1 is going to be equal to 0.9. So I now have this value of 0.9. So what's the rule for that? When the electronegativity value is between greater than 0.4 and 1.7, the bond is described as polar covalent. So it's putting a description on it. And I'm just putting in this caveat, and this is where heads will hurt at a later date. Having polar bonds doesn't necessarily make molecules polar, but we'll talk about that in a while. But in your caveat. So we now have a definition. So this is a rule, have to know it. We now have a definition of a polar covalent bond, and that is unequal sharing of electrons. So the fact that we did this tiny piece of maths over here gave us a number, and that number now tells us that there is unequal sharing of electrons between atoms. So what chemists do to reflect this unequal sharing is they put these little symbols over them. They're called delta plus and delta minus, or delta positive and delta negative, but I will say it as delta plus and delta minus. So that is the Greek symbol. And together, these symbols indicate unequal sharing of electrons, and you're only putting them in because of the values that we just had. So we had 2.1 value here, and we have 3.0. This is the bigger number, this gets the delta negative. This is the smaller number, this gets the delta positive. But together they indicate that there is unequal sharing of electrons. So the delta positive represents a slight, and I will use the word partial, negative charge on the chlorine. So that's why it's got this delta. It's not a full ion, it's just a very slight negative charge. And what that means is that if you were to draw the electrons in your shared pair, they are going to be in this position. They're going to be closer to the more negative element. The delta positive represents a very slight positive charge on the H, and again I will talk about partial positives and partial negatives. And what that means is, as in the diagram, the electrons in the shared pair are further away from the H. So we go back to your definition of electronegativity, the relative measure of attraction an atom has for the shared pair of electrons. So if you have the bigger number, you are more attracted to the electrons, they will be closer to the bigger number. If you have the lower number, the shared pair are not going to be as attracted to you. So I hope that makes sense. So the fact that we have this charge means that there is unequal sharing. And in reality, if this blue here is an electron cloud, and the green is the nucleus for chlorine, and this is the nucleus for hydrogen, the shared pair of electrons are the little pink dots, and they are going to be close to, I don't know why this isn't animating for me now nicely. I'm going to go back. So this is showing you the kind of electron cloud. All of the electrons are over on this side for the most part, so there's this kind of bulge, and because the electrons are being tugged this way, you don't see them as much. So this is the representation that you're going to put up here in your book. You're never going to have to draw this thing with the blue, but it's just to kind of give you an idea that if you could see the electron cloud, it's all over toward chlorine and not so much at the hydrogen. So the electron distribution, when you have these little delta pluses and delta minus, is showing you that you're getting unequal sharing of electrons between your atoms. And when this happens, it's called a permanent dipole. Okay, so that's a real new word. So HCl can be described as a polar molecule as it has a permanent dipole. So what that means is that in every HCl you will have this delta plus and this delta minus. They will exist all of the time. They don't disappear, they don't take a holiday, they are always there. So it's what's called a permanent dipole, and again, when we get onto intermolecular forces, we'll be talking about permanent dipoles. Okay, and so di being two, pole meaning kind of opposites. So in this case, positive and negative, and it's going to always be present. So this may help you. Dipole is a permanent separation of opposite partial charges. So they're not full charges. We're not making ions in here. We're just making a little bit of my molecule positive. We're making a little bit of my molecule negative. And sometimes that can be really hard to get into people's heads. Okay, so we're nearly finished with the notes for today. So here is a list. From this, which covalent bond would you think could be the most popular? Now you can look at page 8 for me, but the key in the question is it's the word covalent. So you have to remind yourself what part of my periodic table is covalently bonded. So in reality, for covalent bonds, the most covalent molecule or most polar molecule that exists is HF. And the reason for that is H is going to be 4. F is 4, hydrogen is 2.2. We've said in terms of our maths, you take away 4.0 minus 2.2, and that's going to give us, what, 1.8? Roughly. Stuart, but you're going, Miss, potassium is 0.8, and you're absolutely right, potassium is 0.8, but potassium is also a metal, and covalent bonds are between non-metals only. So you need to bear that in mind. Okay, now if we look at NaCl, so if you look at your tables on the back of page 8, wherever, sodium is 0.9, chlorine is 3.2, so chlorine is going to be the most electronegative. I should have put up here that if you're drawing this is how you would draw it, and you're drawing it because the F is the bigger number, so that gets the little delta negative, and the H is the smaller number, that gets the delta positive. But going back to NaCl, if we take one from the other, you get 2.3. Now the rule is, this brings us to our final rule. So the final rule is, if you have an electronegativity greater than 1.7, it indicates that it's probably an ionic bond. Okay, now there are some caveats, and this 1.8 up here being 1. HF is covalently bonded. Doesn't always follow the rules. As far as the SEC are concerned, for you, they will follow the rules. So if you are greater than 1.7, so 1.701, you will be an ionically bonded compound. Now, I'm just going to summarize the rules and the types of bonds for you here. So I'm going to get rid of pure, and we're going to call it nonpolar. So a nonpolar covalent bond, you will have your electronegativities will be 0.4 or less. So I'm going to slightly, okay, so 0.4 or less. Okay. To be polar covalent, then you will have a difference in your electronegativity. It'll be greater than 0.4 but less than 1.7. And finally, to be ionic, by using electronegativity, the difference between them will be greater than 1.7. Now, in terms of what you're going to do now for homework is on page 154, it's the top of page 154, you have to predict the polarity in the following bonds, and if applicable, draw in your delta plus and your delta minus. So I'm going to do the first one for you. So S over here is 2.5, Cl is 3.0. If I take one from the other, I get 0.5. According to my rules, this makes it polar covalent. So I would make this the delta positive and I make this the delta negative. So you're going to complete those for B, C, D, E, F and G and tell me polar, non-polar, ionic, and draw in your delta positive and delta negative only if it's polar covalent. So the last little bit of this, I don't know why it's decided to freeze, is you have two worksheets that follow, I believe, on page 155 and page 156. So I will have this in your class notebook. So you're going to give these a go for me. I am on Teams for the duration, or on Zoom for the duration of this lesson. So please, please, please get in touch if you have a question. No question is too stupid. It is only stupid if you don't ask questions. Okay, thank you.